Consider the boost converter circuit. We have this inductor, the single pole double throw switch and the capacitor. Let us see how it operates and the various waveforms. Let me mark this I0, current flowing through the output load resistor, In, current flowing through the input source Vi. Let me mark the voltage across the inductor. This is the voltage across the inductor VL with the common point of the probe placed here and the measuring point of the probe placed here. Now let us discuss its operation and waveforms visually and get some insight into this converter topology. Now I am going to display the waveforms here, and I have split the time axis into 4 parts as before. Now let us say that PT1 is going to be on during DTS period and PT2 is going to be connected during 1 minus DTS period. So let me mark these time periods here on the graph, DTS and 1 minus DTS. DTS and 1 minus DTS together form a switching period TS. So let us plot first the voltage VL across the inductor, and during DTS the pole P is connected to T1. Pole P is at 0 voltage and the other side of the inductor is at VI voltage. So a voltage VI measured positive like this. Now during that period 1 minus DTS, P is connected to T2. So the potential here is V0, Vp, or the pole potential is V0, and this side of the inductor is still Vi. So voltage across the inductor is Vi minus V0. Now is Vi minus V0 positive or negative? We know that the inductor cannot support an average voltage. Therefore, the average voltage has to be 0 in steady state, which means in steady state during the 1 minus DTS portion, there should be a negative voltage so that there is volt second balance. So that can happen because the voltage across the inductor during that period is Vi minus V0. That can happen only if V0 is greater than Vi. So it is automatic that V0 will be greater than Vi in order to have the volt second balance happening. So this will become negative like this, and so on to the next cycle, Vi and V0, Vi minus V0. So this is the voltage waveform across the inductance. So now let us now see the current waveform through the inductance. I am drawing this average current here. This is average current flowing through the input, flowing through the same inductor. And the inductor has 2 parts, the average part and the ripple part. So let me call this In average and let me draw the ripple. I am drawing the ripple as a straight line and it has a slope. V is equal to L di by dt. So the di by dt slope, I have placed it as a straight line, linear fixed slope. The voltage across the inductor is Vi during that time, constant. L is a constant. Vi by L is the slope, which is a constant. And during this time, Vi minus V0 is negative, so it's a falling slope. Vi minus V0 by L is the slope. So it repeats for the next cycle and so on. So this is the inductor current waveform. Next, let us see the waveform of the switch PT1. So let me draw this I average level position, II average, and IPT1, PT1 current flowing from the inductor into this, and when this is open, the inductor current cannot be discontinuous, it starts flowing into PT2. So the inductor current flows through PT1 during the time DTS when PT1 is on. and only during DTS times you will see the inductor current flowing through PT1, otherwise PT1 is 0. Next, let us see what is the current through PT2. PT2. So during PT1 the inductor current flows through like that, and during PT2 during 1 minus DTS the current flows through PT2, and that is same as the inductor current portion during that time. So this is the current through this PT2. Now what is the average of the PT2? Average of the current through PT2 flows through capacitance and through the output load resistance. We know that the average of the current through the capacitor has to be 0. Therefore, the average has to be I naught. So average is I naught. What is the current through the capacitance? The current through the capacitance is this waveform, PT2 waveform, shifted down by the average, because the average cannot be any finite value here. It has to be 0. So we have a 0 average current flowing here in this fashion, where this amount, but the amount by which it has shifted down is I naught. So these are the various waveforms that we see for the boost converter. And using these waveforms, let us find the input-output relationship and the values of the inductor, capacitance, and what goes on to form the single pole double throw switch. Let us now try to find the input-output voltage relationship for the boost converter. So for that, we have to use the volt-second balance equation. So let us apply this volt-second balance. To what voltage? You will be applying it to the inductor voltage. So look for the inductor, look for the voltage across the inductor, which is this waveform, and let us apply the volt-second balance. Now during DTS, this is the volt-second area. We can use the simple relationship of the rectangular area, because this is a constant voltage. So let us apply that. So this is Vi into DTS. Vi is the amplitude, DTS is the width, and this is the area of the rectangle during the DTS period. Now during the 1 minus DTS period, the voltage across the inductance is Vi minus V naught. So this area we will calculate Vi minus V naught into 1 minus D into Ts. Now this area, positive area, negative area should balance out. So therefore that should be equal to 0. I will remove these two variables out of the picture. Now the remaining variables, if you simplify, you have a Vi into D, and you have Vi and V minus Vi into D. So this Vi into D and this Vi into D will cancel out. You have a V naught into 1 minus D, push it to the other side. So you will end up with V naught equals Vi by 1 minus D. Now this is the input-output voltage relationship for the boost converter. Observe 1 minus D comes in the denominator here. D takes on values from 0 to 1. If D is 0, V naught will be Vi. If D is 1, V naught will tend to infinity, but it will not actually tend to infinity. D cannot take value 1, because then this will be permanently on and there won't be switching. So it should be less than, D should be less than 1. So V naught greater than or equal to Vi, and D takes on values between 0 and 1 in this fashion. So this would be the input-output relationship of the boost converter, and because V naught is always greater than Vi, we call this as the boost converter. Let us also obtain the current relationship. We could use the amp-second balance across the capacitance, or like we did last time, we could use the power balance. Pi is equal to P naught, and therefore Vi II is equal to V naught I naught. Now this V naught, I know from the old second balance relationship is this much. Let me substitute that. VI is equal to Vi by I minus D into I naught. I'll remove these two variables, and therefore you have I naught II is equal to I naught by 1 minus D, and this is the input output current relationship. You could also get the same relationship if you take the amp second balance or the charge balance, find out the area of IC here and find out the area of IC here, equate them and get the relationship. But it is not as straightforward because it's a trapezium, and find that trapezium area, we need to know these heights. Finding this area is easy because this is a rectangle with height I naught, but may be difficult to find this in a straightforward manner. So we use this current relationship, we obtain the current relationship using the power balance, which is much easier. Now let us find the values of the components L, C, and then identify the switch elements of this single pole double throw switch. So first the L. Consider the inductor L. What is its value? Take the inductor current waveform, and we know that the height of this current ripple, let us set it as delta IL. Now this is the change in the inductor current. So we will use the Faraday's equation. V is equal to L di by dt, and we know the slope of this Vi by L. We have written here Vi minus V naught by L for this part of the slope. So consider that during this DTS period, there is a change of delta IL. So di by dt will be delta IL by dTs. So delta IL by dTs is equal to what slope rate, which is Vi by L here in this period. So we will write that down, Vi by L. Or I could take 1 minus d into Ts period. So during that the current is falling. So there is still a change of the same delta IL, though negative slope. 1 minus d Ts equals Vi minus V naught by L. Vi minus V naught by L. So this is a negative slope. The change in delta L is negative in the sense that it's a falling value. So you can take absolute values for finding the value of L, because L has to be positive. You can take, instead of Vi minus V naught minus Vi. Anyway, when you substitute for V naught, all will boil down to the same equation here. And let us take that equation and find out L. So L, I will push it there, delta IL will push it down here, so it's Vi. D, I will push it up there, delta IL. Ts, if I push it up and then say Ts is equal to 1 by Fs, then I can put Fs in the bottom here, denominator. So this is the relationship for finding the value of L for the boost converter. Here you know Vi. Vi is the input spec of the unregulated DC source. D, how do you find D? We know V naught. V naught is again an output spec. So knowing V naught, Vi, we can use the input output relationship and find D. Fs is the designer parameter. At what switching frequency are you switching these switches? It could be 20 kilohertz, 50 kilohertz, or 100 kilohertz. So whatever the designer fixes, specifies, so that will be the switching frequency here. And delta IL, now here IL, unlike in the case of the buck converter, the average value of the inductor current was I naught. In the case of the boost converter, the average value of the inductor current is the input current average. So 10% of this input current average will be delta IL. How do you know the input current? We know VI, we know P naught. P naught and Pi are same, and therefore Pi by Vi will give you II. So 10% of that will give you delta IL. So all these parameters are determinable from the specs, and you can find out the value of L. Next, let us find out the value of the capacitor C. For that, we have to look at the capacitor current waveform, and we know from amp second balance that this area, the top portion of it above the zero line and the bottom portion of the area below the zero line, they should match. Okay. Now the area under this IC curve will be the charge Q. So in every cycle, this amount of area will be delta Q. So let us use, like in the buck converter case, we will try to find what is delta Q. And delta Q we know from physics is C into delta V. So what is delta Q? It is the area. It is the area covered under the IC curve, IC envelope. In this case, between 1 minus d into Ts period and dTs period, it is much easier to find the delta Q of this, because this is a rectangle of height I naught and width time width dTs. So therefore delta Q, I will replace it by I naught. I naught is the height of this rectangle, and the width of that in the time scale is dTs. So that is equal to C into delta V. Now C we can write it down as I naught into D. Ts I will take it to the denominator as Fs. Fs is 1 by Ts, and delta will come down, delta V will come down into Fs. So this is the relationship for the capacitor value. Do we know I naught? I naught is obtained from the output spec. Whenever a power supply is designed, P naught is given, P naught and V naught are given, the voltage of the output and the power that needs to be delivered to the output. D can be found from the input output voltage relationship. Fs is a designer parameter. Delta V is again an output spec. What should be the output voltage ripple? And using that, find out the value of C. So this is the basis for the design, of the C for the boost converter. Now let us select the switches for the single pole double throw switch and find out the ratings. So the switch elements, like we did for the buck converter, we will use the static characteristic for the switches, the IV characteristic. So consider first PT1. Let us consider the switch PT1 and then afterwards PT2. So let us say we draw the IV characteristic of VPT1 and IPT1, and then let us match the requirement with a practical switch characteristic and then select the component. So now if you take IPT1, current flowing from P to T1 is IPT1 positive. And if you look at the operation of the circuit, when P and T1 are closed, the current IL flows in this direction from P to T1. You can also observe IPT1 wave shape here. All are positive. There is no negative component of IPT1, which means there is no current flow from throw 1 to P. All current flows are P to throw 1. So only the positive current axis are potential operating points. So let us mark that. So these are potential operating points, meaning that PT1 should allow positive direction of current flow from P to T1. Now for the voltage when the switch is off. When the switch is off, what should it support? What is the voltage of P, pole P? So when T1 is off, P and T2 are connected. So P and T2 are connected, the output voltage will come at this pole point. So the pole voltage will become V0. V0 is positive. T1 is at ground potential. So PT1 is a positive voltage, and the switch PT1 during off condition should support or withstand a positive voltage, which means all the positive voltage points on this axis become possible potential operating points. So we expect a switch to have this kind of a characteristic, and we saw while we were discussing the buck converter that it is similar to a BJT or a MOSFET characteristic, or even an IGBT. So I can use a BJT or a MOSFET here in place of PT1. And for PT2, let us draw the IV characteristic, VPT2 and IPT2. So looking at the inductor current, we know that the current used to flow from P to T1, and then when you switch off PT1 and connect to PT2, the current has to flow from P to T2 in this direction. And you can also look at PT2 current waveform. All are positive, there is no negative, meaning there is no current flow from through to P. So therefore we can say that all the positive current axis can be potential operating points. Now when the switch PT2 is off, meaning when P is connected to T1, during that time PT2 is off, what is the voltage it will withstand? T2 is at V0 potential, P is at ground potential when P is connected to T1. So PT2 is negative, and therefore you will see that it has to withstand all possible negative potential. So this character is provided by a diode. So therefore PT2 should be a diode. Now let us replace this single pole double throw switch with the selected types of the switches, let's say BJT or MOSFET, and the diode at their respective places. So let us erase some portion of this PT1 and then introduce a BJT. Wherever I have introduced BJT, you can as well introduce a MOSFET or also an IGBT. All are valid switches in those places. They are controlled switches. So I have put this BJT in here to match for this characteristic requirement. Then this PT2 we said matches a diode, so we will make some space there and introduce this diode here. So let us clear up, this is called Q and this is D. So this becomes the complete topology of a boost converter with the semiconductor switches in place. What are the ratings of Q and D? So let us say Q, the ratings of that. So first the voltage rating, VCEO rating. So during the off condition, what is the voltage that Q has to withstand? During the off condition, the inductor current is passing through the diode to the output. So the diode is conducting. So V0 comes as the pole voltage here. So Q should withstand at least the V0 amount of voltage. So VCEO should be greater than V0 definitely. Then what should be the max current rating? ICM rating, collector current max rating should be greater than. Here you see in IPT1, this point here is the max current that occurs, and that is I in average plus delta IL by 2. So this is I in average plus delta IL by 2. And I in average can be related to the I0 current. We know we developed the input output current relationship where I is equal to I0 by 1 minus D. So therefore let's say I0 by 1 minus D is this I in average plus delta IL by 2. So in terms of known items. D is known, I naught from specs, delta IL by 2 is known. You can say what should be the current max spec for Q. I naught by 1 minus D plus delta IL by 2. So for the diode rating, we have the peak inverse voltage. Peak inverse voltage should be greater than what? So when Q is conducting, the diode D is off and it is seeing the peak, the inverse voltage. So during the time when Q is on, the pole point is connected to the ground. So pole voltage is 0 and the diode's cathode is connected to V0. So therefore, at least V0 amount of reverse voltage the diode has to withstand. So it should be greater than V0. And ID maximum is like here. You have IPT2, the max point is same, I naught by 1 minus D plus delta IL by 2. So all other currents like average and the RMS currents can be calculated from the wave shapes. So this would be the way you choose the ratings for the semiconductor switches of the boost converter.